Hi, everybody. My name is Cedric. You've met Wolfgang already online, and I'm going to talk to you about, sorry, let me move this, about finite elements and especially in geodynamics. So a bit of background first. If you looked at some version of the geodynamics.org website some time ago, you would see all these codes there. And if you look at the ones that are highlighted with the red arrows, you would find that they are actually powered by the so-called Q1P0 element. Don't worry, I'll explain this in a minute. And not only these codes, but also the ones on the right. So you have Sopal, Dwar, and a bunch of others. And as far as I'm aware of, more than several hundreds of papers have been written with this finite element. Then we have the so-called Q1 stabilized, and it actually powered the infamous Gale code, but you will also find it in the groundbreaking work of the RIA code some 10 plus years ago. It was also featured in my own code in 2018, so that's Elephant, and then I found also an occurrence in the work by Nestor Serpa in 2015. Then we move to the so-called Q1 and Q2P-1 element pairs, and then these are the ones that we can find in aspect, the Q2Q1 being default. And also they are the Q2P-1, as far as I'm aware of, is the default in P-Taten, which is another modern, massively parallel geodynamics code. And of course, if we're not using what,
Cedric,
sorry?
hang on for a second. Can you move that the zoom control bar at the top somewhere to the right?
Oh, yes. Sorry, actually, I thought you guys didn't see that.
Yeah, it covers the title.
Yes.
Okay, thank you.
Oh, okay. What happened there? Oh, okay. Is that good now?
That's good. Yes.
Okay. Sorry about that. Okay. So we have right. So I've listed all the quadrilateral elements that are used in geodynamics. And of course, we don't have only quadrilateral elements in finite elements. We can also rely on triangles or tetrahedra in 3D. And I've highlighted here a few publications that do so. So we have commercial software console. If you go back to 2008, there is the Milliman code in MATLAB. Then more recently, the La code from 2019. On the bottom left here, we have fluidity. And on the bottom right, we have dinosaur. I believe this is how you're supposed to pronounce it, right? So we have quite the variety of elements in geodynamics. And so one would be tempted to conclude that, well, we can just pick any elements and basically do science, pick any code, do pretty much anything you want. But no, as you can imagine, not really. So before I embark on telling you what Wolfgang and we did, I need to introduce a few notations, right? So when we're talking about these, so Q2, Q1, Q2P-1, that sort of thing, the first letter with the first number actually indicate the polynomial that is used to represent the velocity inside an element. And the second one, so this Q1 here in this case, is the polynomial used to represent the pressure inside the element. And so in this case, Q2 stands for second order. And the Q stands for the fact that it's actually a second order polynomial in each direction. So effectively, we have in the x direction, we have x and x squared. In the y direction, we have y and y squared. And then we have the product of all these terms. So you have all these, cross product here, x, y squared, y squared. So that's your Q2 polynomial. The Q1 is the same thing, but now only to the first order. So we have the term in x and y and the product thereof, x, y. Now the P actually here stands for a different type of polynomial. In this case, here I've represented the P1. And you see that there is no cross, so there is no product of x and y, right? So this is a complete polynomial to degree n. It's not a product of multiple ones. And if n is 0, like in Q1P0, then effectively you have a piecewise constant pressure, right? So, and we omit the minus sign. The minus sign, I forgot to mention, indicates that the pressure is discontinuous, right? If you're interested in this, well, I guess the presentation will be online somewhere, and I have links here that, to to justify this. Okay, so the four elements I was talking about at the beginning of the talk are the Q1 P0. So this one has a linear velocity and a constant pressure. The Q1 Q1 stab, this one has the same polynomial for velocity and pressure, but it's notoriously unstable, so it's been stabilized. So you need to do something to this the linear system that we've seen before. And here we have the more costly ones. So the Q2 Q1, this one has 9 velocity nodes, but has this Q1 pressure. That's the default in aspect. And the Q2 P-1 has the same velocity nodes, but it has a P1 representation of pressure, and it's discontinuous from element to element. And you can switch between the two in aspect by using this set use locally conservative discretization and set it to true. So these are the four elements that we tried and tested. So in 2022, we got a paper accepted in Solid Earth. And effectively what we did is implement and or allow these four elements in aspect. We ran multiple benchmarks. We looked at the so-called convergence rates. We compared, the results for all four, and we drew conclusions. And more recently, we just resubmitted some 6-7 weeks ago already at the second part of the paper, where we actually investigated now triangles effectively. And so what we did is to actually implement and allow all four triangular elements that I will talk about in a second. And we compared them against the two best quadrilateral of the first paper. And we did that in our own Python code. Ran the same benchmarks, look at the same quantities, these convergence rates, and then compare results, quads versus triangles, and again, drew conclusions. And effectively, just to give you an idea of the content of these papers is here you have the so-called Donea and Huerta benchmark, which you will find in aspect. It looks something like this. This is the velocity field, and the pressure field is this parabolic field. This is a manufactured solution, right? This is not necessarily something that's very geodynamical, geophysical, but this is a case where we know the analytical solution to. And so that means that we can, as a function of the mesh size here, so the size of one element, going from coarse to quite refined from right to left, we can look at the error between what aspect computes, so the velocity of aspect, UH, and the analytical solution. And mathematicians have proven that we can expect certain rates of convergence for different types of elements. And the first thing we did was to actually confirm that our rates were following what we expected. So here I have the results for the velocity. And what we see is that the Q2, Q1, Q2 P-1 elements converge, like h cubed, like cubic, and the other two converge like h squared, quadratic. That's for the velocity. And for the pressure, I have a quadratic pressure convergence for the Q2s if you want. I have a linear one for the Q1 P0, and I have something in between, so order 1h to the power 1.5 for the Q1 Q1 stab. This was no news at all, something we expected that had been published before, so there was some kind of confirmation that everything was good to go. Then we run another benchmark called the Sol CX benchmark, also in aspect. And this one is characterized by a viscosity field that is 1 on the left and 10 to the 6 on the right. And with this very sharp discontinuity here in the middle. What happens is that effectively the solution is discontinuous. And when we look at the velocity here, same thing. So the velocity error as a function of the mesh size, we recover virtually the same plot. So this one is not that interesting. Here it's a bit more interesting because we see that the Q2 Q1, which has a continuous pressure, this Q1 term here, actually fares pretty bad, right? It's actually below the blue, which is the Q1 Q1, and converges like h to the power 0.5. And that is also not new. It was published in the first aspect paper, Krumbishler et al. 2012. And this is because this pressure is continuous while the analytical solution, once is actually discontinuous. And so the one that fares here the best is the Q2P minus one, because the viscosity discontinuity is aligned with the mesh. So again, this was what we expected. We also ran the Sol VI, so inclusion benchmark. I'm not going to talk about it. It's in the paper. More important, what we actually did is to run the sinking block experiment. Not a benchmark per se, but this is a more like a interesting test case. And so you have a 512 times 512 kilometer mantle with very simple free slip boundary condition. And the block here in the middle is marginally more dense than the surrounding, right? So d rho over rho is 0.25%. And it can be either isoviscous or more viscous or less viscous than the surrounding. And what we actually do here is run this system with the Q2, Q1 and the Q2P minus one. And on the left and the right here, you see that the solutions for the velocity are pretty much identical. But when we look at the velocity field obtained with the Q1, Q1 stab, then this is using the standard full density mode. And you see that there is a huge problem. There is virtually no velocity in the block here. Well, here we have some kind of gradient. So this is pretty bad. And when we tried almost like a trick, which is removing the background lithostatic pressure by removing a constant density value, we kind of recover the signal, but also it was not accurate enough. And this is, mind you, this is already at a rather high resolution, right? So if you would extrapolate it to 3D, that would be very costly, meaning that the Q1 stab is pretty much is not usable in this case. And then I'm turning to the pressure that we measure exactly in the middle of the block as a function of the viscosity ratio between the sinker and the fluid. And what you see is that pretty much for all elements, that normalized pressure falls on one line, except for the Q1P0. And the issue is that the pressure is discontinuous from element to element. And on top of it, it's plagued by a so-called spurious checkerboard mode. So in essence, the pressure here inside the block has, showcases these red values. And this is bad news because A, it's far from what the others are giving me. But also if you think about the fact that the pressure is needed in our material models, so for plasticity and viscosity, having this checkerboard mode is a very big problem. You can filter that, but this is unfortunately a feature, if you want, of the Q1P0. And finally, what we did in paper one, we took actually the version of the aspect extension cookbook from a few years ago. It's changed by now. And we have here on the left the results obtained with the Q1 stab versus on the right the results obtained with the Q2 Q1. And you see that here at the bottom, I have these weird artifacts, right? It's very visible here in the strain rates. Of course, it propagates in the viscosity because it's, I believe it's dislocation creep here. And so once again, in a geodynamical context, the Q1 stab rules itself out. So the preliminary conclusions and the conclusions effectively of paper one were that only the Q2 Q1 and the Q2P minus one are acceptable or even usable, right? The other two are out of the question. And so what we ended up doing in part two was to say, okay, well, we're going to keep these two quadrilaterals, and we're going now to test 4 triangular elements that we found in the geodynamics literature, right? Here we have pretty much the cheapest one, which is the so-called P1 plus P1. So it has a velocity bubble in the middle and a velocity and a pressure node at each vertex. And it is kind of dependent of the Q1 stab, right? It's almost the same kind of some cost if you want. Here we have the P2P1. So it's quadratic for velocities and linear for pressures, and it's dependent of the Q2 Q1. Here we have a discontinuous linear pressure case, but you have to add a bubble, so this extra node in the middle, to make it stable. And that's kind of the triangular version, if you want, of the Q2P minus one. And then we tested a fourth one, which is the P2P0. So it's actually quadratic in velocity, but it has a constant pressure inside the whole triangle. So it's kind of, if you want, like the Q1P0. And of course, when you use triangles, you need to think about the mesh a bit more than with quadrilaterals in this kind of calculations. So when we use quadrilaterals, well, we just use a regular grid, which we can subdivide like this to make it usable for the triangular elements. These are the structured grids. And then, of course, what you can also do is do tests on so-called unstructured grids, right? So here, this would be some kind of randomly generated grid that is such that the average element size is comparable to this one, right? And for the viscous inclusion, what we did is we actually adapted the mesh to the inclusion here, right? So we actually forced these edges to be exactly on the inclusion. And I think sometimes visuals are very important. So here is actually the pressure field that we obtain running the inclusion benchmark. So here's the inclusion. The pressure is supposed to be 0 in it and have this under pressure and over pressure field there and there. This is, yeah, like I said, the pressure field. So you see that between the P1 plus P1 and the P2 P1, we have, well, slightly different results. But what is really interesting here is that in the so-called, so this P2 plus P minus 1 is sometimes called, it's also called the Cruiser-Raviar. It doesn't much matter. But because the pressure now is allowed to be discontinuous, and in this case, I haven't really matched it to, I haven't matched the elements to the inclusion, what you get is these huge spikes, right? So inside each element, you have a pressure field that is linear, but discontinuous from triangle to triangle. So this is not necessarily good news. Again, in the context of using pressure in rheology, this could yield rather large problems. We tested again the Donea and Huerta benchmark, and I'll spare you the details. We actually recovered all the expected rates from the literature. I will draw your attention to the fact that here we have the structured mesh results, and we have the unstructured mesh results here at the bottom. And what you will see is that the worst elements, the ones that showcase the largest errors, are actually the P1 plus P1 and the P2 P0 consistently. And all the others converge with the expected rates, so I'll spare you the details. We ran the Sol CX benchmark. Again, the P1 plus P1 and P2 P0 were shown to be actually, their errors were actually rather high. Their convergence rate were also as expected, but much higher. And what is rather interesting here is that, again, the Sol CX showcases a discontinuity in the middle. So as soon as we look at the pressure, this element, the Q2, Q1, as before, ends up here with a convergence of h to the power 0.5. But also, this guy, the P2, P1, the orange one, also has a continuous pressure, and so ends up right there, right? And the ones which fare the best are the discontinuous pressure ones. So the Q2, P minus 1, the P2 plus P minus 1 here, and the P2, P0. And what we see here is that the quads here outperform the triangles. And again, running the sinking block benchmark, we have the same setup, and I'm measuring the same thing. So you're looking at the pressure in the middle as a function of the viscosity ratio. Again, I would expect or hope that all the results to actually align on this curve here. And I have two large outliers. This is here for a 64-64 mesh, right? And the worst ones are the P1 plus P1, so this one here. If you increase resolution, you see that the blue line slowly will tend and converge to the yellow one and the others. That will take very high resolution. And again, because the P2, P0 has a discontinuous pressure from element to element, you have these changes, these values. And the only way to bring that error down is to increase resolution, but to the point that you'll pay a very high price if you want to have all the red dots on this line. So again, the conclusion here is that the P1 plus P1 and the P2, P0 are not suitable, okay, and if you care about more of these results, we've run more benchmarks, we do more measurements, and we show more figures in the paper. Like for instance, this Rayleigh-Taylor wave. We showcase all the convergence rates, and I was looking today at the download rate. It seems that people actually like it. There is still some interest in the paper, so I hope it will get published soon. But the conclusions are that, fortunately for aspect, but obviously not really big news, the Q2 Q1 and Q2 P-1 are the best compromise for robust mantle convection and crustal dynamics. Their counterparts are the cheaper Q1 P0 and Q1 Q1 stab actually disqualified themselves because they're just not accurate enough for buoyancy-driven flows. I've shown you that their triangular counterparts, so P1 plus P1, P2, P0, also same problem. They're not accurate enough, especially in buoyancy-driven flow. That leaves us with this family, some people call that the Taylor-Hood family. They're accurate and they're robust, and they're the cheapest that are accurate and robust. And you will find that these are the backbones of all modern codes in geodynamics at the moment. We don't prove it, but we expect our conclusions to hold in 3D. We also do some studies and we show that per degree of freedom, the quadrilaterals are found to be slightly more accurate than their corresponding triangular versions. Something to bear in mind is that unstructured meshes introduce complexity, right? You need to mesh. What we take for granted with P4est, we would have to have a different library that handles meshes and refinements, that sort of thing. So there is some cost associated to it. And I'm curious to hear from the deal.II people how things are going with respect to the implementations of triangles in deal.II that is currently going on. And maybe someday in aspect, but still we should ask ourselves the question, why would we want triangles in aspect to start with? So with this, I'll leave you with this. Thank you.
All right, well, thank you, Cedric. We can discuss the triangle question at the end of the session. I think in the interest of time, let's move on to Kieran. And then if there's time, we have till 45 past the hour to discuss. But we also have only one talk in the next session, so there's plenty of time for more discussion. So Kieran, you want to go ahead?
Yeah, let me share my screen.
All right, take it from here.
Right. Okay, well, thank you for the invitation to give this talk today. Today, I thought I'd walk through my paper that was published last year in Geophysical Journal International called Effects of Using the Consistent Boundary Flux Method on Dynamic Topography Estimates. I would like to thank our co-authors for their many contributions they made to this work, and also acknowledge National Science Foundation and USGS for funding this project. I will begin with a brief introduction, briefly describe our methods, discuss our dynamic topography results, and the geophysical implications of our results on the East Coast of the United States. And finally, I will wrap up with a few concluding remarks. Some basic concepts, dynamic topography versus tectonic topography. So with dynamic topography, a hot, low-density anomaly in the mantle will rise, resulting in dynamic uplift, while a cold, high-density anomaly will sink, resulting in dynamic subsidence. the amplitude and wavelength of dynamic topography will be in proportion to the intensity, timescale, and depth of mantle flow. In contrast, positive tectonic topography is the result of plate convergence, which causes crustal and lithospheric thickening, while negative tectonic topography is a result of plate divergence, which causes crustal and lithospheric, which is caused by crustal and lithospheric thinning. So while the theory of dynamic topography has been well established, there remain discussions about which components of mantle density and flow should be included in the definition of dynamic topography signal. So processes that contribute to dynamic topography include lithospheric isostasy, sublithospheric isostasy, and mantle flow. In this study, we define dynamic topography as vertical surface deflections induced by surface stresses, which includes the whole mantle, including all the processes that are shown in this panel. With aspect version 2.0.0, a consistent boundary flux method, which is used to compute dynamic topography, was implemented into the code. So one objective of this work was to assess the influence of the CBF method on dynamic topography estimates. Further, we aimed to analyze some potential geophysical implications of the improved estimates for instantaneous, present day, and rate of change of dynamic topography solutions on the US East Coast. The Farallon slab, which is approximately 100 million years old, currently lies beneath the east coast of the United States. This has been imaged with seismic tomography, which is shown here on the right. And it has been proposed that the cold, dense slab is inducing mantle downwelling, promoting negative dynamic topography. However, this hypothesis is still heavily debated. So we use aspect version 2.2.0 to model dynamic topography. I'm sure most of you are familiar with this, but the driving equations for viscous flow modeling, assuming compressible flow, are the momentum and mass equations. These constitute the compressible Stokes system, where U is the velocity field, P is the pressure field, rho is density, eta is viscosity, G is gravitational acceleration, and epsilon is the strain rate. Dynamic topography is computed using a stress balancing approach where radial stress is balanced by excess topography using this equation for H, where sigma represents radial stress, which is calculated using this equation, where G hat is gravity, and then P sub D is dynamic pressure, which is adiabatic pressure subtracted from total pressure. Aspect, and then aspect version 2.0.0 implemented the consistent boundary flux method, which calculates radial stress at the surface. So now the current version of aspect, or aspect 2.2.0, and versions of aspect prior to the release of version 2.0.0 use these same equations to compute dynamic topography. However, the CBF method computes dynamic topography with higher accuracy because it incorporates boundary integrals, including the normal stress, which allows the normal stress to be computed on surface boundary nodes. It's been estimated that the CBF method improves the accuracy of dynamic topography estimates by an order of approximately 1 magnitude. Our simulations are use the model setups following Osterman et al. 2017. So we test 3 initial temperature conditions: Texas 2008, S40 RTS, and Savani. The density perturbations for the 3 temperature models is shown here on the right, which was taken from Lee 2020. The material model we use is primarily adopted from Glisovich and Forte 2015. We employ 4 different radial viscosity profiles, 2 for Texas 2008, V1 and V2, which are largely similar in the upper mantle, the main difference being this low viscosity notch in the transition zone in V1, which is used to uncouple the upper and lower mantle flow. For tomography models S40 RTS and Savani, a depth-dependent viscosity profile is chosen specific to each tomography model, and those are from Steinberger 2016. We impose a radially varying gravity profile from Glisovich and Forte 2015, which is shown here on the right. So all 4 Earth models, that would be Texas paired with V1, Texas paired with V2, and then S40, RTS, and Savani, are all tested with both a no-slip and free-slip boundary condition. So that gives us a total of 8 different model setups. Moving on to our results. Here we are looking at the total global average across all 8 model setups for instantaneous, present day instantaneous dynamic topography and rate of change of dynamic topography since 3 million years ago with the CBF, without the CBF, and then those residuals. The average rate of change of dynamic topography since 3 million years ago is computed by subtracting instantaneous dynamic topography estimates at present day from estimates at 3 million years ago, and then dividing that result by 3 million. So in these figures, the blues represent subsidence and the reds represent uplift. The highest magnitudes of uplift are marked with A and B for both present day instantaneous and rate of change. And then the highest magnitudes of subsidence are marked with C and D, which you can see here. So for both instantaneous present day and rate of change of dynamic topography, we observe a trend of spatial similarities with generally higher magnitudes and estimates of dynamic topography calculations with the CBF algorithm implemented, which you can see based on the ranges here for present day and rate change of dynamic topography with versus without the CBF. And when we look at present day instantaneous and rate of change of dynamic topography, just on the East Coast, again, we observe sort of the same patterns with spatial similarities, but higher magnitudes using the CBF method. Again, you can see the ranges here kind of indicate that. The average percent change for instantaneous present day dynamic topography is approximately 25%. So I'll discuss a couple of the geophysical implications that we investigated. One, we investigated how dynamic topography predictions and with and without CBF can affect the interpretation of the Orangeburg Scarp. So the Orangeburg Scarp shown here would have been horizontal at the time of formation, but it now shows up to 60 meters of variations in elevation. And this warping is thought to reflect post-mid-Pliocene elevation changes due to dynamic topography, glacial isostatic adjustment, as well as contributions from flexural isostasy due to sediment loading and erosional unloading. This figure here shows our computed change in dynamic topography over the past 3 million years with the CBF, without the CBF, and then the residual. The cumulative change in dynamic topography over the past 3 million years at the peak, which is the Norfolk Arch, with and without CBF is 69 meters and 47 meters, respectively. So these differences in estimates of dynamic topography changes can significantly alter the interpretations drawn from the mid-Pliocene shoreline that's preserved in the Orangeburg Scarp. This figure here shows change in dynamic topography since 3 million years ago, kind of following from south to north along the Orangeburg Scarp, with and without CBF, these red and orange lines, respectively. The shaded regions show the standard deviations of dynamic topography changes with and without CBF between our 8 model setups. So note they are quite large. As a reference, we also include the elevation changes of the mid-Pliocene shoreline, accounting for GIA, and assuming a 14-meter eustatic sea level difference between the mid-Pliocene and present day. And that was taken from Rovere et al. 2015. Our peak elevation change, which occurs about at 36.4 degrees north, with and without the CBF, is approximately 68 meters and 43 meters respectively. So this 25-meter difference in elevation change can lead to vastly different interpretations of the mid-Pliocene shoreline. A greater change in dynamic topography would lead to different, would lead to, these different interpretations of the shoreline as well as past sea level changes. And this would also suggest that a smaller contribution to the warping of the Orangeburg Scarp from isostatic processes, such as glacial isostatic adjustment and flexural isostasy from sediment transport, would be required to explain sort of the present elevation of the scarp. And then one other geophysical implication we looked at. So Osterman et al. 2017 computed vertical deflections due to dynamic topography to compare with a global set of last interglacial sea level markers. And they found that predictions of changes in dynamic topography since 125,000 years ago were correlated with patterns in LIG sea level marker elevations, but the magnitudes of predicted changes were overall lower than observed changes. So we evaluated the distribution of changes in dynamic topography on the US East Coast over the past 125,000 years, with and without the CBF at these LIG sea level markers, used from the compilation from Osterman et al. 2017. So that's what you see here on the left. The mean dynamic topography changes over the past 125,000 years with and without CBF was about 1.84 with CBF, and then 1.07 meters without CBF. So this result suggests that one possible reason for the misfit between the magnitudes of dynamic topography changes and observed sea level changes in Osterman et al. 2017 is a result of dynamic topography being computed using aspect prior to the implementation of the CBF method. So those are a couple of the geophysical implications we looked at. And then I'll just wrap up with a few concluding remarks. So to summarize, we ran simulations with and without CBF for the 8 different experiment setups using tomography models Texas 2008, S40RTS, and Savani. each tested with a specific radial viscosity profile for Texas 2008, and then these were tested with 2 different boundary conditions. Dynamic topography results showed similar spatial consistency in both approaches, but an increase in magnitude for both present-day instantaneous dynamic topography and rate change of dynamic topography since 3 million years ago, using that CBF method. Differences in dynamic topography change along the Orangeburg Scarp can significantly alter the interpretations of mid-Pleistocene shoreline and therefore past sea level changes and ice sheet stability. And the enhanced accuracy in dynamic topography calculations can be used to better evaluate the effects on surface processes, including vertical motion, sea level changes, as well as sedimentation and erosion, to name a few. So that's all I got. Let me stop sharing.
All right. Thank you. So we have 4 minutes for questions, but we have only one talk in the next session. So Poulami, if that's okay with you, we'll just take questions until we're done, and then start with your talk. Is that okay?
Yeah, it's fine.
Okay. So then questions. Let me see. John.
Great. Thank you both, Cedric and Karen, for the great talks. I had a question for Cedric about the Q1 P0 element. And basically my question is this is the element that Underworld uses, but they have a slightly different approach to aspect, is where they use particles for the integration points. And I can't remember, and basically my question is I know they somehow modified the Q1, or like with their approach, they don't see these pressure instabilities. And I was curious if you know how they did that.
I wish. Yes, I see exactly what you mean with their Voronoi integration-based thing for the particles and stuff. I am still puzzled as to what they're actually really doing with this inside this code to get the Q1 P0 to work for them, whatever that means, like in terms of solvers, in terms of accuracy and all that. To be honest, I never really meet anybody who's using this code or would know enough about the insides, because it's mostly in Australia, I believe. So I have never really had the chance to ask Louis, I guess, or Kenneth or others. No, I can't really, I can't answer your question, but I wish I could. If anybody knows, Wolfgang, do you have ever talked? No? Okay.
I have no idea.
Okay.
We should ask Louis at some point. Wait, quarter Louis at a meeting, because I know it's somewhere from back far in my mind. They had done something with their approach to stabilize the element and reduce crest oscillations. All these years later, I'm still curious what they did. But thank you, Cedric. Great talk.
Thank you.
Thanks for doing all this testing. It's incredibly useful.
Sure.
Renee?
Yeah, thanks both for the talks. I have actually questions for both of you, but since we were talking about elements, Cedric, you showed that the quad elements could get better accuracy per degree of freedom. Did you look into performance at all? Because 1 degree of freedom in a quad element might be more expensive than 1 degree of freedom in a triangle, because it couples to more degrees of freedom. Did you look into this at all, or did you just not look into this?
Well, let me share my screen for a second. Can I do that? Yes. You see that?
Yes, I do.
Okay. So this is a quick, I knew there would be a question like that, so I did a screen capture of the paper like 20 minutes ago. We actually looked at this. Actually, I believe because one reviewer wanted to have this information as well. And so the figure above, sorry?
It wasn't me.
No.
But yeah, okay.
So yeah, we looked at, so on the left, the time to build the linear system, and on the right is the time to solve the linear system. Although the time on the right, I'm using a direct solver, so it doesn't really, it's not really that exciting. On the left is, the time to build the matrix, and you see that it's not really, can I zoom in? Yeah. Oh, I lost it. Okay, sorry. Okay, don't touch it. Yeah, so they all pretty much fall on the same line. There's not a huge difference. A big caveat is that my code is absolutely not optimized at all, right? It's right. So the timings, there's nothing in there that is optimized effectively. So all the times I report here are way not impressive in that sense. So it's more like the trend that is somewhat meaningful. And when you look at per degree of freedom, or a bit here, this is per element size, you don't see much of the big difference in terms of yeah.
Okay, good to know. And Karen, I wanted to ask, so it's pretty cool to see these like practical consequences of having a more accurate or less accurate numerical method. I didn't quite catch how you computed the difference in topography between today and earlier times, because it looked like you were running kind of like an instantaneous model with these seismic tomography models as background. Do you evolve them forward in time or backward in time? How did you do that?
You need to unmute yourself first. There you go.
Yeah, so they're moving forward in time, starting at 3 million years ago.
But we don't have a tomography model for 3 million years ago. Do you just use the tomography model from today at that time, essentially saying it was the same 3 million years ago? I mean, it probably didn't change too much. So
I think, I'm trying to remember. It's been a couple years since I was
that would mean you would
diving
essentially
into
assume
what
that
these different models look like.
that the rate of change between today and 3 million years in the future would be the same between today and 3 million years ago, which is probably not a bad assumption, but
yeah.
That is exactly what we decided.
What we
yes.
Okay. Yeah, I mean, it makes sense. It makes sense. Thank you.
Action.
Okay, so I have two questions, and the first one is for Cedric. So when we run the numerical models, I think a common question is that whether we should use higher order elements with a coarser mesh, or the lower order elements with a higher refined mesh. So Cedric, what's your opinion about this? I just wonder. So how do you compare the accuracy of solution between the higher order mesh with a coarser mesh and the lower order elements with a more refined mesh? Which one you will prefer? Yeah.
So effectively, what we did is we actually argued against the low order ones because either they're not stable or they're not usable.
Even do you mean even we increase the refinement for the lower order elements?
Yeah. So effectively we removed the ones that were not usable, and then arguing for using Q3, Q2, or even higher actually makes little sense, because very often our solution, because of plasticity or very sharp transitions, I guess melt would come in there and whatnot, the solution would not really lend itself to be represented better by these high order polynomials. So I guess what Aspect is using now in p-Taton and fluidity are these elements that are stable, usable, but also the cheapest in the sense that anything lower order would just not be accurate enough.
So basically, you are even argue against the usage of lower order elements, even with the higher refined mesh than the higher order elements. Correct?
Yeah, because in practice,
because it's because even with a higher refined mesh, it still has the issue of the accuracy of solution with the lower order elements.
Yeah, and there's also the fact that, for instance, to name it, the Q1 P0 is notoriously unstable, and that has consequences for the linear solvers too. Right, so technically, on some of my plots for the Donea and Huerta, the Q1 P0 stops abruptly because actually its aspect solver didn't converge.
Okay. And so how about the same question, the comparison between the, for example, Q3, Q2, and Q2, Q1. Both are stable. Which one you prefer? The coarser mesh with Q3, Q2, or the more refined mesh with the Q2, Q1, for example? Yes.
I think for practical reasons, I would go Q2, Q1 because of these unpredictable high viscosity contrast. So your solution basically is, yeah, I'd rather represent my solution in 2 times Q2 than 1 Q3, right? Like the union of 2 second-order polynomials rather than 1 cubic polynomial for the whole thing.
Oh, so you will prefer the Q2, Q1 element in the practical application for the our use, correct?
Yeah, I
So
mean, to
you
be fair,
will-
we
so
really
you will-
investigate. I mean, we did not
Yes.
investigate Q2, Q1 and the like against higher order. We just said, well, the lower orders are now not cutting
Okay.
it. That's mostly the conclusion.
Okay, I see. And my second question is for Karen. So I wonder when you calculate your output of the topography, you will need to first transfer your velocity model of your tomography to buoyancy field. So I wonder when you do it. I wonder when you do your transfer for this kind of calculation, how do you deal with the velocity? How do you deal with the sudden velocity in shallower region in your 4 different tomography models? I mean the velocity. I mean the velocity anomalies in the shallow region, in the top 200 kilometer or top 300 kilometer. How do you deal with that? Did you keep it as it, or you just remove it from your tomography when you do your scaling translation?
Okay, I kind of caught some of that, but my Zoom is a little bit messed up. So your question was how to handle the velocities at the surface in the tomography models? Is that
My question is that when you want to calculate the output of the topography, you should first translate your seismic velocity tomography model to buoyancy or density variation. And when you do this, how do you deal with the buoyancy at shallower depths at top 300 kilometers, for example, in your models? Did you just use a constant scaling factor for that, or you just remove it from your models? Yes.
so we worked with Jackie Osterman, who kind of parameterized the like continental lithosphere a little bit from the Savani and S40 RTS, and that was based off the and I know that was based off like the parameterizations that they use in Steinberger 2016. I'm having a little bit of trouble remembering like the actual details, the differences. But yeah, I think it's basically, yeah. So it follows Steinberger 2016, I think.
Because for example, when people are doing this kind of a translation, because the cretins in the shallow region has lots of chemical buoyancy, so people commonly just zero out the buoyancy of the cretin area. So I wonder, did you do the similar thing, or you just keep it as it is, and then do a simple translation of this?
I think Shangan trying to say is there might be other parameters that can affect elastic waves in addition to temperature. right? Especially at shallow depths.
Yes, and then I wonder whether there are some treatment of this in your model. Yeah, that's my
But
question.
I think the answer is, I think based on her assumption, it means dynamic topography is created by temperature variation, and seismic variation is directly related to those temperature differences. This is the main assumption her calculation is rooted in, as far as I understand. Am I right, Karen?
Yeah, that's right. Yeah, temperature to density through
Yeah, it could
the
be
formulation in Steinberger 2016. Yeah, sorry.
So
yeah,
it's
sorry, can I also add, Shengshin, she's not taking the seismic velocity models just straight as they are for the upper 200 kilometers for all of them. She follows what Jackie did in 2017, which, as Karen said, for the continental regions, she does something a little bit different. But Karen, you don't recall exactly what she did for the continental regions?
Yeah, I'm kind of blanking. I'll follow up with you, Shengshin.
Yeah, because I mean, for the region of the Cretan or for the region of the continental area, if you just do a simple scaling transfer from the velocity model to the density variation, you will have some overestimation of the buoyancy on that region. Yes.
Let's leave it here. And the two of you can coordinate, and maybe Karen, you can send him the paper. And
may I? It's last one.
Yeah. Ibro, you had your hand up, and I couldn't tell whether it was I have a question or whether it was an applause.
I have a question, but I don't know how my hand. Where is my hand? I don't see.
Well, do you want to ask a question?
Yeah, and just little comment. Can I do that?
Yes.
Okay, so thank you, Karen, for your presentation. It was beautiful. And I'd like to say that you may not be in the safe zone in terms of calculating backward, especially in orogenic regions. So, and I was wondering your opinion about the seismic perturbation, but I'm gonna skip that, and we'll contact with you. And thank you.
Yeah, I do want to, like, we did emphasize in the paper that we're not really suggesting that our final results using the CBF is the Mantle convection model used for dynamic topography. We just wanted to illustrate some of the differences between CBF and no CBF, and kind of illustrate how much of an impact kind of something as seemingly simple as that can kind of lead to different interpretations, geophysical, like, from a geophysical, more practical standpoint.
Okay, so I think this might be a good time then to move on. Thank you, Karen. Thank you, Cedric. Poulami, you want to take it over from here?
Yeah, sure. Thanks.
Okay. Thank you for your patience.
Can you see the presentation?
Yeah, just fine. Yes, go for it.
Okay. Hi everyone. I am Poulami Roy. So first of all, I would like to thank the Aspect community for giving me this platform to showcase my work. This work is part of my PhD work, which is understanding lower mantle anisotropy from plume generation. And in my PhD, I have worked with Bernhard Steinberger, Manuel Facenda, Mikkel Pons, and this work has been benefited from very helpful discussions with Aspect developers. So to start with, I want to give you the idea of Burkean Earth. So the famous geologist Kevin Burke first proposed that upper mantle and lower mantle are coupled with each other. So you see here that the upper mantle slab can penetrate in the lower mantle, and from the core mantle boundary, mantle plumes or upwellings have been generated, and it can come up from the lower mantle towards the surface and erupts the hotspot volcanism. And one of the very interesting feature of Burkean framework is that he proposed these kind of deep mantle plumes are associated or generated at the margins or boundaries of the large scale structures. These he named them large low shear velocity provinces. So I think you appreciate the fact that the flow pattern in this area is kind of complex because the mantle flow here has been influenced by sinking downwelling slab, and also it has been influenced by upwelling and the geometry or the dynamics of these large scale structures. So this is sort of the motivation of doing this work, where we wanted to address the question that can we constrain the mantle flow at the core mantle boundary where upwelling has been generated? And the another question is, can we constrain the geometry of the LLSVP piles in the core mantle boundary globally? So what we know about this LLSVP pile from seismic tomography is that these piles have been detected by negative shear velocity anomalies, meaning that these are hotter regions, hotter than the ambient mantle. And the active hotspots and large igneous provinces that we see on the surface, they are mainly associated or positions at the vicinity of the margins of these piles for both of the cases, for the African LLSVP piles and the Pacific LLSVP pile. But what we don't infer is the mantle flow pattern from this isotropic shear velocity anomaly. So here comes the importance of seismic anisotropy. So I very quickly go through the concept of seismic anisotropy for the people who are not familiar with this. What seismic anisotropy means, it's basically a phenomenon of seismic wave. When seismic wave passes through an anisotropic medium, it splits and travels in different orthogonal directions. So one wave becomes faster, shown here by the blue curve, and another becomes slower, shown here by the red curve. And depending on their depending on their arrival time difference and the orientation of these splitted waves, seismologists can measure different anisotropic properties of the medium. So the cool thing of seismic anisotropy is it is an observation. Now, why do we care about seismic anisotropy on mantle dynamics? So we all know that mantle is made up of rocks. Rocks are made up of minerals, and minerals are made up of crystals. Now, what mantle flow does, it induces deformation and aligns the mineral crystals in preferential orientation. So this kind of preferential orientation that has been induced by mantle flow is called lattice preferred orientation or crystal preferred orientation. Now, once this situation has been achieved, the medium becomes anisotropic, and then seismologists can measure anisotropic properties that I have mentioned in the earlier slide. So there are several anisotropic properties one can measure, and here in this work we are mainly consider radial anisotropy. What does it mean? It is actually a ratio between horizontally and vertically polarized waves. And in this work, we consider the shear wave component of seismic wave. So the idea is that when radial anisotropy is positive, that means the horizontally polarized shear wave is faster, which means the horizontal flow dominates. And if it is negative, it means vertical flow dominates. So the bottom line is that we really cannot go to the core mantle boundary and see the flow pattern, but we can compute or simulate the radial anisotropy. From there, we can infer the mantle flow pattern. Now, how do we set up the workflow from geodynamic model to the seismological modeling? So for simulating the convection pattern, we use aspect. And from aspect, we compute the velocity, pressure, temperature fields. And that we input to ParaView. And using ParaView's Python calculator, we homogenize the grid. And we also do time step specific export of geodynamic data for each time step. And then we take the output from ParaView Python calculator and input it to MATLAB to reshape the data in order to make it compatible with the final seismological software that we use here, that is EcoMan. EcoMan has been developed by mainly Manuel Facenda and others. And now EcoMan and Aspect can use a same structure of per place lookup table. So in this way, they are coupled. And from EcoMan, we can compute the lattice preferred orientation of mineral crystals. And it also has got some modules which helps us to visualize the computed anisotropic properties in gridded format. So what is the initial setup of the geodynamic model? So our models are 3D global spherical, and this is a slice of the global model. So here each quadrant shows different properties starting from temperature, density, and viscosity. So we also prescribe our core mantle boundary temperature 3800 Kelvin, and we have prescribed an adiabatic temperature profile having a top thermal boundary layer and a bottom thermal boundary layer. Density is modified PREM density, and for viscosity, we use initial Steinberger radial viscosity profile. And on top of that, at the base of the lowermost mantle, we prescribe a 100-kilometer thick, flat, compositionally distinct LLSVP layer. And keep in mind that initially our LLSVP is a flat layer. And then we use Aspect's adaptive mesh technique in order to refine more to the hotter regions and the colder regions. And in this way, we can refine our mantle plumes at 11 kilometer. So the 11 kilometer is the resolution of the mantle plumes of this model. And this is the boundary condition that we use in this model. So we use 250 millions of years plate motion history that has been taken from G-plates. And why 250 millions of years is because our models are kind of developing the mantle plumes, which have been generated as an influence of subducted slab. And around 250 millions of years, Pangea started breaking apart and subduction becomes a dominant force in mantle convection. So that's why we chose this time frame. So our models are forward model. We started our model 250 millions of years back and let the model run towards present day. Now we see the evolution of these of the reference model, and different color here means the blue, red, and yellow are depicting the slab, mantle plumes, and LLSVP composition. So I play the video here. So initially it is a flat layer, and then as subduction has been started, it pushes the bottom thermal boundary layer, and the flat LSVP becomes pile-shaped, and eventually at their margin, mantle plumes have been generated, which also entrains the some LLSVP material within their conduit. So here you see that the Chilean subduction zone has been forming. And yeah, so this is the final present day configuration that our model predicts. So here we look into a detailed mantle configuration at present day. So what happens is that the, our model nicely fits with the present day Chilean subduction zones. And at the western part of this, the Pacific plumes have been generated from the specific LLSVP. Interestingly, at the African LLSVP, the plumes are having a broad base. These are called sheet-like upwelling. And at the vicinity of the margins of this African LLSVP, mantle plumes have been forming. So now here I'm showing the evolution of the LLSVP pile from an initial flat layer at 2,800 kilometer. So the model starts 250 millions of years back when all of the continents are together, as you can see in the background of this figure. And I let the model run. So from an initial flat layer, a pile kind of geometry started to form. This is the present configuration of the piles that the model predicts. So now we compute the radial anisotropy from these geodynamic models. So the base fit model that produces negative radial anisotropy, which means that around these piles, the mantle flow is mainly vertical, and away from these piles, the mantle flow is mainly horizontal. That has been detected by positive radial anisotropy. Now, if we compare our modeled anisotropy with seismic anisotropy observation, we see that there is a first order match between modeled anisotropy and anisotropy observation. But in the observation, we do see that inside of the piles are also having negative anisotropy or vertical flow, but in the modeled anisotropy, the main upwelling regions have been accumulated at the margins of the LLSVP, not exactly at the inside of these piles. And the base fit model has also got a strong LLSVP, meaning that it has 100 times more viscous and 2% denser than the ambient mantle. Now we also tested different, now we here I'm showing that different depth slices starting from 2,800 kilometer to shallower level. So what we see here is that at the very base near the D double prime, these piles are, these upwelling regions are more pile-like. And then if we come towards shallow level around 1100 to 800 kilometer, this shape changed from pile-like to sheet or reed-like. And that has been detected by negative radial anisotropy. So at shallower level around 700 kilometer, this structure becomes plume-like, and the base fit model produces 14 mantle plumes. So the mantle plumes here have also given by nearest hotspot location. And then we compare our modeled plume with seismic observation from French and Romanovich 2015. So our model predicts 14 mantle plumes, and the observation of French and Romanovich, they have got 11 primary plumes and 9 clearly resolved plumes. So our model's result is kind of like in between from what they have got. And then we have also tested different model variations having different densities and viscosity ranges of this LLSVP layer. But all of the cases here, we do not really consistently produce upwelling zones or negative radial anisotropy throughout the LLSVP. So from there, we kind of predict that the previous model is the best fit model, which is having 100 times viscous LLSVP. Now, this is the summary of this work. Here we try to build a global pattern of radial anisotropy, which shows that at the very base, at the core mantle boundary, the mantle flow is horizontal. That has been detected by positive radial anisotropy. And this flow is deflected at the rheologically stiffer LLSVP piles, which makes the mantle flow vertical. Which has been detected by negative radial anisotropy. The red zones and upwelling have been generated from these areas. So here we try to build a model which kind of depicts the Barkian framework in a more realistic way, such that it incorporates it incorporates seismic anisotropy as an observational constraint, and we believe that we predict the global mantle flow, specifically in the lowermost mantle, where observation is even more scarce. So this work is incorporated in my PhD thesis, and my thesis is published now. So if you are interested, you can go and have a look on my thesis. And I would like to give a big thanks to the Aspect developers and maintainers. With them, I have a very fruitful discussion, technically and scientifically. And this is a picture of 2023 Aspect Hackathon, which I have enjoyed a lot. So I'm going to stop here and would be happy to take questions. Thank you.
Very nice, Poulami. Thank you. We've got time for questions. Go ahead. Oh, here we go. Renee, yes.
Hi, I didn't want to be the first to speak again, but since everyone else is sorting out their questions, Poulami, you know that my PhD topic was pretty similar, and so I was trying in my mind to compare the models that you were running with the results that I saw, and I noticed that interestingly, the shape of your LLSVPs is slightly different from the one that I saw, and the only real difference methodically, like except for the anisotropy part which you added, is the plate reconstruction that you used, right? You used the Murdoch 2021. And I was wondering, did you compare different plate reconstructions at some point during your thesis, and what kind of influence they had, especially on the shape of the African LLSVP? Because I remember that earlier studies, both that McNamara and Jean paper in 2008, or when it was, and also in my studies, we had kind of this coherent African LLSVP, and then some other studies, and also including yours now, show this separation into this ridge-like structure in the Atlantic, and then like a little separate piece under Africa. Did you compare, directly compare different plate reconstructions in one model to see if that is what's causing this difference?
Yeah, that is a very interesting question. No, I haven't done this testing, but I think this plate reconstruction plays a very important role, because this kind of bifurcated African LLSVP, which I was also wondering, and then I checked the 2019 Flament paper where they used this recent plate velocity, and they also mentioned that these plate reconstruction driven geodynamic models are actually producing this kind of bifurcated LLSVP. So I think it might have an effect which I haven't tested. But then I ran one of the best fit model for more than 250 millions of years, and I see that around 440 millions of years, this bifurcated part has been joined with the main African LLSVP. So,
so you mean you have run it further into the future with the present day plate motions?
No, it's kind of like I after 250 millions of years, I restarted the model again from 250 millions of years. So it's
okay.
Restart model. And so the total time span I'm saying is 440, but it's not from G plates 440 millions of years. So it's 250 and then restarted. And then we see that that there is a that these two piles can be joined with each other. And the Steinberger and Torsvik 2012 GQ paper, they have actually tested this restart model, where they show that this kind of restart model can actually produce more number of mantle plumes that is more consistent with seismic observation. So there can be two things. One is that I can start the model for more G-plate velocity, like more than 250 millions of years G-plate velocity, and G-plate construction variation. I think that these two are important parameter. I mean, these two are the important like constraints we can check.
Yeah, I think this is interesting that the plate reconstructions have such a large influence on the outcome of these models. Yeah, but great, thank you.
Jeroen.
Yeah, thanks, Poulami. That's very nice. one question I wanted to ask is how long it takes to develop the seismic anisotropy in the models. So basically is it the seismic anisotropy you measure now is basically almost like only affected by the last few time steps in your model to develop the seismic anisotropy, or is there a much longer memory of that also the flow fields of say 50, 100, 200 million years ago will still affect the seismic anisotropy you measure today?
Yeah, very cool question. Actually, it affects. So the result that I have showed is the anisotropy calculation has been done with the LPO formation for the last 20 millions of years. And then I haven't showed the result, but it is in my thesis. If we let the model run for longer time, we kind of develop more anisotropy inside of the chemical piles. So for longer run, we can develop the anisotropy inside of these piles, because these piles are kind of stiffer, so they don't want to be deformed easily, and that's why the more deformation is at the boundary if you model if you compute this anisotropy for shorter time scale. But one of the difference that we have seen for longer time scale is that then the piles are also inside of the piles are also showing or deforming and producing anisotropy. But another cons of this very long-term model is that then the model becomes too much anisotropic, like the surrounding mantle becomes too much anisotropic, which is not very consistent with tomographic observation. So that's why I think last 50 millions of years would be good if you want to compare it with present day instantaneous tomography observation, because ultimately we compare it with the tomography that we see now. So yeah, so I checked with 20 millions of years, 50 millions of years, and 250 millions of years. And these are kind of differences that we have seen.
Interesting. Yeah. Okay. Thanks very much. Yeah.
Thank you.
Sarah.
Thank you so much for the really interesting presentation. I was wondering if you put some thought into some of the recent papers that have come out about the LLSVPs potentially having partial melt in them and how that could affect the anisotropy signals. I don't know, and maybe future directions for the modeling work, given that those newer hypotheses about partial melt down there.
Yeah, that's an interesting point. I mean, I haven't tested partial melting inside of the LLSVP yet. The recent seismic observation also said that this partial melting has been occurred inside of the ULVZs, the ultra low velocity zones, which are also at the boundary of the LLSVP, but these are very small scale structures, the ULVZs. And I'm not very sure in global model if we can do this ULVZ refining or not. But I mean, that's a good point. Maybe that's a good point of doing future research of incorporating partial melting. But on the other hand, we can say that then if we include partial melting, then the mechanism of anisotropy becomes different than LPO. So we have to include shape preferred orientation. And one of the Pachenda's paper of lower mantle, he showed that mainly the lower mantle does not have an effect of SPO anisotropy modeling. So it mainly causes the anisotropy mainly has been caused by LPO, not very much from the SPO. Even if it has a very insignificant amount of anisotropy contribution compared with LPO contribution. So I think it's a good point, but I also think it does not change the result that much.
Okay. Yeah. Cool. Thank you.
Thank you.
Okay, Jeroen, back to you.
Sorry, I didn't. I just forgot to take my hand down. Sorry, I didn't have another question.
Well, do we have other questions? Adam?
Hi, I have well, firstly, I thought it was really interesting, so thanks for the great talk. I was just wondering whether you've thought about kind of or whether it'd be worth also using azimuthal anisotropy and maybe in the same model trying to compare with shear wave splitting. I know it's pretty difficult for the seismologists to get measurements down there, but I've seen a few papers where they're using shear wave splits to kind of try and figure out how the regime of the flow kind of along the side of the LSVPs. So I guess I was wondering whether that would be is that something that can be done technically and whether it, just a thought as to whether that might be worth thinking about. Maybe there's some richness that you can get when you combine both the kind of, anisotropy tomography with the actual shear wave splitting to get at the radial and the kind of azimuthal lateral dynamics.
Yep, we are working on it. We are working on anisotropy. And the thing is that since this work's main aim is lowermost mantle dynamics and LLSVP geometry, but for lowermost mantle, we don't have that much seismic observation from azimuthal anisotropy. Mainly, it's from the global whole mantle radial anisotropy tomography model. That's why we kind of chosen this radial anisotropy as the main target, main anisotropic parameter. But we are actually also working on azimuthal anisotropy. So we can simulate and model from the software. Now, in order to comparison, the observation is really scarce from azimuthal anisotropy.
Okay, yeah, that makes sense. And then just another quick one while I have you. So I think I missed it in the talk, but what was the strength of the LSVPs, and could they be could that be what's kind of causing this kind of ridge-like structure? Did you test higher strengths? I probably missed it, but
so for strength, we mainly tested different viscosities, compositional viscosities. Now, for these, do you mean why we get the ridge-like structure, or
yeah, and I guess thinking about whether that could be due to low viscosities, and just more curious about what viscosity ratio you used. I think I probably missed it from the talk.
Oh, I see. So no, I mean the base fit models, we actually considered 100 times viscous LLSVP. These are also compositional viscosity, but again at the lowermost mantle we have this thermal boundary layer, so that actually decreases the overall viscosity. Now I have a profile of different density, different viscosities. So if you see here at E, the subfigure E, here you see that we have tested different viscosity models. So the black one is the ambient viscosity without having any higher viscosity LSVP. But then we also increase the viscosity 10 times higher and 100 times higher. In case of 10 times higher, here it becomes actually less than the ambient viscosity because of the temperature effect. But 100 times suits best because it actually it actually gives the higher viscosity than ambient mantle. Yeah, so we tested we tested ambient viscosity LSVP, 10 times higher LSVP viscosity and 100 times higher viscosity. And the 100 times is the best fit model that we found.
Right, thank you very much.
Thanks.
Okay, maybe last question, maybe?
Yeah, maybe it's not worth it as a last question. It's a minor detail, but can you show the video again of the 3D model? I noticed something there that I wanted to ask you about. And it's mostly that sometimes here, for example, can you pause? at this point already, we can see the ridges in these models, but you probably label temperature isocontours here. Is that right? So the reason we see these ridges is because you prescribe velocities at the surface and you generate a lot of shear heating at these ridges because of the high viscosities there. And I just wanted to say, for your study, it probably doesn't matter, but we ran similar models where we wanted to look at long-term thermal evolution of the mantle. And there it matters if you generate all of this additional shear heating at the surface. And so there is an option, I think Juliana implemented that now, to limit the stress in the uppermost layer if you prescribe these velocities at the surface. So it might be worth, if you want to run these models for longer, if you ever want to look at the long-term temperature evolution, to limit that stress at the surface to prevent this additional heating generated there. Because in the real Earth, you would just have much lower viscosities at the ridges, and then you wouldn't have this additional heating.
Yeah, that's a good point. I mean, I actually tested one of the models with Juliana's implementation, but I don't know, at around 240 millions of years, the model crashed, and I got in couple of points, not everywhere, like 3-4 mesh points, the viscosity gives me NaN value, and yeah, so I could not manage to run the model for 250 millions of years. But I was trying, so I would be very happy to have a very successful model which incorporates this limit shear heating mechanism.
That's good to know. Like, we should look into that and see if there's something causing these NaN viscosities.
Yeah.
Well, thank you.
Sounds like a bug. If you can come up with a simple example, please please post that. Let's see if we can figure out how to make that work. So we're at 12:30, which the program says is the end of this session. We have another hour, I think, from 1 to 3 o'clock, 1 to 1:30 my clock. No, from 1 to 2:30 my time, where we can have discussions. How do we want to do this? Who wants to be here? And or should we have a goodbye word from our master of ceremonies, Renee, now? Renee, do you have an opinion about this?
I think it's probably easiest if we kind of conclude the official part of the program now, and everyone who still wants to chat, feel free to rejoin in half an hour, and we'll see if there's still something to talk about.
Let's do that.
So I guess then at this point, thanks everyone very much for participating in this year's Aspect user meeting. Big thank you to Lorraine for handling all of the registrations and website on CRG. Big thank you to all of the chairs for chairing the sessions. Big thank you to all of the speakers. I think we had really great presentations this year, as every year really, but especially this year. And to everyone participating, asking questions and using Aspect. It's been fun. Thank you very much, and see you next year, hopefully.
All right, and so if you do have questions, come back in half an hour. We'll see who's here then.